All right, in this video, we're going to talk about suggested homework problems from 2.6. These are related rate problems. Related rates are a special type of implicit differentiation where we differentiate with respect to time, which we'll use the variable t for that. Both, well, all the other variables that we see in our equation, we're going to assume are changing with respect to time. So we'll get to some word problems later that will make more sense what we're talking about, but we're usually talking about things that have some kind of growth rate or velocity or something like that that we are interested in. So let's look at 3y equals the square root of x that I'll write as x to the 1/2 power, and I'll differentiate here and say dy dt is equal to 1/2 x to the negative 1/2 dx dt. Again, differentiating implicitly with respect to time. One final rewrite here, dy dt equals 1/2 root x times dx dt. If I wanted to solve for dx dt, instead of dy dt, dx dt is equal to 2 root x times dy dt. So I have the setup now for both parts of my problem. Part A asks me to find dy dt given x equals 4 and dx dt is equal to 3. So dy dt is equal to 1/2 root 4 times 3 is going to be 1/2 times 2 times 3 is 3/4. For part B, we're given that dx dt is what we want to find. So x equals 25 and dy dt is equal to 2. So dx dt is equal to 2 root 25 times 2. dx dt is 2 times 5 times 2. So dx dt is 10 times 2 is 20. We don't have any units given in this first problem, but it'll be important to include the units for our rate of change when we know it. So that'll be coming later again, mostly with those word problems. So that was number 3. We're going to move on now to the next problem, which is number 5. So 5 says that y equals 4. So I can write that as x equals y/4, or that can be written as y equals 4/x. I might need those given one of the variables. I might need to solve for the other one here in just a minute. So let's differentiate. If I want to find dy dt, I'll differentiate, or dy dt, I'll differentiate this last one here. dy dt is equal to, and I'm going to think of this as 4y to the negative first, and this is 4x to the negative first. So that's going to be a negative 4x to the negative second times dx dt, or that's a negative 4/x squared times dx dt. All right, so for part A, we have that. And so we want to find dy dt given x is equal to 8 and dx dt is equal to 10. Make my substitutions. Dy dt is equal to a negative 4/8 squared times 10 will be a negative 4/64 times 10. 4 goes into 64 16 times. And then we have a common factor of 2. 2 goes into 10 5 times. 2 goes into 16 8 times. And I end up with -1 times 5 is -5 in the numerator. 8 times 1 is 8 in the denominator, for a rate of change dy dt of -5/8. For part B, I'm going to differentiate this middle piece here. Dx dt is equal to a -4y to the -2nd. dy dt is equal to -4 over y squared dy dt. You may have noticed that you can just rearrange things here in the other problem, and that's good. So I'm given x and I need to find y. So it might have been beneficial to go with this form where I was given x. I'll just leave this as it is. I'm gonna make a substitution here that y is equal to 4 over x, and x is being given to me as 1, and dy dt is being given to me as -6. So if x is 1, y is 4 over 1 is 4. So we've got that. Dx dt is -4 over 4 squared times, and then dy dt was -6. So 4 goes into 4 squared 4 times. So that's a negative 4, -1/4 times -6 over 1. Negative and a negative make a positive. This is 2 goes into 6 3 times, 2 goes into 4 2 times, and that's a rate of change of 3/2. All right, the next problem that we have to look at is number 9. So we're told to that a point is moving along the graph of the function given at the rate dx dt that's given to us, and find dy dt for the given value of x. So very similar to what we've just been doing. Just this is talking about particle motion now. So y equals tangent of x, dx dt equals to 3, and they've given us units now of feet per second. That's going to be important. So dy dt is going to be equal to secant squared of x times dx dt in all 3 of these parts. Let's look at part A. Is x is equal to a -π/3. So dy dt is equal to secant squared of -π/3 times dx dt is 3 feet per second. So dy dt, this is just going to be a number. These units won't change, and dy dt will also be in feet per second. Now remember that secant is an even function, so it doesn't matter. This negative is going to it's going to be symmetrical about the y-axis, since it's an even function. So I can say that this is the same thing as secant squared of π/3 times 3 feet per second. That's just an even odd identity. All the functions are odd other than cosine and secant, which are even. So for an odd function, f of -x is equal to -f of x. for an even function f of negative x is equal to f of x. Don't forget that from pre-calculus. So secant of pi over 3 is related to cosine of pi over 3. So cosine is 1/2. The reciprocal of 1/2 is 2. So this is going to be dy dt is going to be 2 squared times 3 feet per second. And dy dt is 2 squared is 4 times 3 feet per second. And dy dt is equal to 12 feet per second. Part B, x is equal to a negative pi over 4. So dy dt is secant squared of negative pi over 4 times 3 feet per second. Dy dt is equal to, so cosine of pi over 4 is √2/2, but that also can be written as 1/√2. That's more helpful here so that I can find the reciprocal. So the reciprocal of that is going to be √2. Again, I'm ignoring the negative because of the even function. I'm just thinking about secant of pi over 4 right now. I'm squaring that and multiplying by 3 feet per second. So dy dt is 2 times 3 feet per second is 6 feet per second. Part C down here is x equals 0. So that's dy dt is equal to secant squared of 0 times 3 feet per second. So cosine of 0 is 1, reciprocal of 1 is 1. So this is dy dt is equal to 1 squared times 3 feet per second is 1 times 3 feet per second is 3 feet per second. So that was number 9. Let's look now at number 11. We start to get into more of the word problems here. A radius r of a circle is increasing at a rate of 4 centimeters per minute. So dr dt equals a positive 4 centimeters per minute. Find the rate of change of the area. So we're talking about area of a circle. A equals pi r squared. So you got to know all those geometry formulas for this section here. And then we're going to differentiate with respect to time. We see time in the bottom here. So dA dt is equal to 2 pi r dr dt. The area is changing because of the change in the circumference and because of the circumference at the time and the change of the radius at the time. That's why the area is changing. So, so dA dt is what we want to find here. And this is going to be when r equals 37 centimeters. So I've got my calculator ready to help me with some of these messy calculations. And the book is going to want to keep all of the answers in terms of pi. So unless told otherwise, do not round your answers. 37 times 4 is going to be 148 times the 2 that's on the outside is going to be 296. So dA dt is equal to 296 pi. Centimeters times centimeters is centimeters squared. Per unit of time here is minute, and that's dA dt. Moving on to number 13 for volume. Thirteen says that the radius of a sphere is increasing at a rate of 3 inches per minute. Well, they tell us we're talking about volume, so we're talking about volume of a sphere, which is 4/3 pi r cubed, and dv dt is going to be 4 pi r squared times dr dt. This 4 pi r squared is the equation for the surface area of a sphere. If you ever need it, you might. So we're given that we want to first find the first want to say that dr dt is equal to 3 inches per minute. So that's given to us. Then we want to find the rate of change, dv dt, when r equals to 9 inches. And then again, when r is equal to 36 inches. And I don't like when they do multi-part questions and then they ask you multiple parts in each little part. I think that's hard to notate. So, but anyways, this is going to be dv dt is 4 pi 9 centimeters squared times 3. Why did I say centimeters? 9 inches squared, 3 inches per minute, like that. And inches there, clear. dv dt is 4 times 9 squared times 3 is 972 pi. And then you have 1, 2, 3. You have inches cubed per minute. That makes sense. That's a unit of volume. In cubic units, that's a unit of time. So that's what I expected. So 972 pi cubic inches per minute. When r is equal to 36, I have dv dt is equal to 4 pi times 36 inches squared times 3 inches per minute. 4 times 36 squared times 3. And I think you see why I have the calculator. I don't want to do that by hand. dv dt is equal to 15552 pi inches cubed per minute. 15552, yes. Part B asks, explain why the rate of change of the volume of the sphere is not constant, even though dr dt is a constant. So looking at my formula here, if I have v equals 4/3, I'm sorry, dv dt is equal to 4 pi, and say dv dt is, or dr dt is a constant that I'm just going to call c, times r squared, and r and t are my only variables. 4 pi c is a constant of proportionality that I can call k. So that makes dv dt directly proportional to r squared. You may remember that from a long time ago in math, that you talked about things that were directly proportional and inversely proportional, and you had a constant of proportionality k, and that the things on the left side were proportional to the things on the right side. They're directly proportional to the things that were changing in the numerator and inversely proportional to the things that were changing in the denominator, things like that. So the r squared is in the numerator here, and it's directly proportional to dv dt, and dv dt is directly proportional to r squared, meaning that if r squared increases, that dv dt will increase. If r squared decreases, then dv dt will decrease. So just because this one part of the equation is constant doesn't mean the whole equation is constant and that there's going to be a zero rate of change. All right, let's look now at the next problem, which is 15. And it's also about volume. It's volume of a cube. So volume of a cube, we're going to call side cubed. And the sides are changing at a rate of 6 centimeters per second. And then dv dt is going to be 3s squared times ds dt. Part A asks what dv dt is when s is equal to 2 centimeters. So dv dt is 3 times 2 centimeters squared times 6 centimeters per second. Don't think I need the calculator for that one. 3 times 4 centimeters squared times 6 centimeters per second. That's 12 times 6 is 72 cubic centimeters per second. Might want the calculator for this one though. When s is equal to 10 centimeters, then dv dt is 3 times 10 centimeters squared times 6. Yeah, I'll still be good with this one. 10 centimeters per second. So 6 times 3 is 18 times 100 square centimeters. I've still got centimeters per second over here. dv dt is equal to 1,800 centimeters cubed per second. On to number 17. All right, so this is nice that they give you the equation here, but you're going to need to know if you get a problem like this on a quiz or a test, that when we talk about a gravel pit or a sand pit, or that they're dumping gravel into or sand into something, that it's going to naturally form this conical pile that as you pour it in, it's going to kind of slide down the sides, and the base is going to get bigger and it's going to get taller. And I'm just telling you that this is the case with a cone, that there is a ratio between the height and the base, or the height and the radius, and they're going to give us enough information to figure out what that ratio is, because you're going to need to write your equation for v in terms of just a single variable, and either with respect to r or h, but you need to read the problem to figure out what kind of substitution you need to make. So at a sand and gravel plant, sand is falling off of a conveyor onto a conical pile. So they're telling you it's a conical pile, but it's going in at the top here at a rate of 10 cubic feet per minute. The diameter of the base of the cone, so diameter, which is 2r, is 3 times the altitude. So the altitude is the height they're talking about, h. At what rate is the height of the pile changing? So I want to get it in terms of h, so I want to solve for r to eliminate r from my equation. So r is 3/2 h, or 3h over 2. When the pile is 15 feet high, h is 15 feet high. and they give you the volume of the cone is 1/3 pi r squared h. So I need to write that in terms of h. R is 3/2 h. I'm going to square times h, 1/3 pi, and that's 9/4 h squared times another h. 3 goes into 9 3 times. So V is 3/4 pi h cubed for my volume in this situation, where I have a cone with that relationship of 2r equals 3h. So I'm going to differentiate now. dv dt is equal to 9/4 pi h squared times dh dt. And what did they give us? They gave us dv dt was 10 cubic feet per minute. And they gave us the h was 15 feet. And they want us to find dh dt. So 10 times 4 is 40 over 9 pi. I'll just leave that like that for a second. Is 15 squared is 225. This is square feet. This is still cubic feet per minute times dh dt. So when I divide cubic feet by square feet, I'm going to be left with feet per minute. And then I have, this is 9 pi, and this is 1 over 225 is dh dt. So there's some simplification that can be done there. I'm going to definitely just leave the pi alone down there. And I've got 40 divided by 9 times 225. And I want to change that to a fraction, is 8 over 405. And then this is feet per minute is what dh dt is. And that makes sense to me that height is measured in feet and time is measured in minutes. And that's my most accurate measurement for my rate of change. Looking now at number 19, this is a pretty complicated problem. It's going to take some time, but this is pretty real. So you don't have a swimming pool that has a shallow end of 0 depth. When you get in, it's always got a shallow area that starts off gradually and goes down. It usually is like 3 feet, which is about a meter. So that's what they're saying there, is that it's going from about 3 feet deep to about 9 to 10 feet deep here at the deep end. If that helps you with thinking of that as a standard swimming pool that you have measured in feet. And it's coming in at 1/4 of a cubic meter per minute. That's not going to be as easy to change into cubic feet or cubic inches or anything like that per minute, but just leave everything in meters here. But take a look at how I have 2 different pieces here. On the top, I'm going to have a rectangular prism that there's this piece that's going to look like this on the top of the wedge. And I'm terrible at drawing, so I'm sorry, but there's a nice little rectangular piece sitting there. And then I've got a wedge that right here at the bottom, let's see if I can draw right here, that right here where I'm drawing the blue line that's down the 1 meter right here. So this is at 2 meters right here. So this is going to be 1 meter tall, and it's going to be 6 meters in this direction, and it's going to be 12 meters in this direction. This wedge is still going to be 12 meters this way, but it's going to be 2 meters deep this way, and we don't need the slant distance, but it's there, and it also goes back 6 meters. So, right, like that. So we'll need that. I just want you to see the two pieces, that there's a wedge like a doorstop, and there's like a box that's on top of that, and that we're going to need to find the two volumes of those pieces independently, and we're going to need to add them together in this problem to find the total volume. All right, so dV dt is given as 1/4 cubic meter per minute. For the box here, we're going to be asked a question about the what percent of the pool is filled when I have this little wedge down here that is like so, that is 1 meter high. So I have my dimensions here, and this 6 meters doesn't change. That's the width of the pool the whole time. But these are similar triangles. They have the same angles to them. This angle is the same. This angle is 90 degrees. This angle has to be the same. And when all the angles are the same, they're in proportion. The triangles are in proportion to one another. So I cut 2 in half to get 1. I'm going to cut 12 in half to get 6 again. So then I have a volume formula for a wedge that says take the area of this right triangular face and multiply it times this dimension that goes this way. So the volume of this wedge is 1/2 of my base, 6 meters. This base is 6 meters times this height of 1 meter times this dimension that goes this way, this third dimension that will be 6 meters. So that's going to be 3 times 1 times 6 is 18 cubic meters of water that I have in the pool right now. The volume of this wedge here is 1/2 of this base of 12 times this height of 2. Do this down here. Volume of the wedge is here 1/2 base of 12 meters, height of 2 meters, and width there 6 meters is 6 times 2 is 12 times 6 is going to be 12, 2, 6, 12 times 12 is 144. And that divided by 2 is 72. All right. And then I have a volume here of the prism, this is called, the rectangular prism, length times width times height. So this is 1 meter times 6 meters times 12 meters is 6 times 12 is 72. So total volume of the pool is going to be 72 plus another 72 is 144 cubic meters. With all that information, I'm ready to answer part A that asks me what percent of the pool is filled. So 18 cubic meters divided by 144 cubic meters times 100% is going to be 18 divided by 144 times 100 is 12.5%. I hope that really helped you to see all those drawings, especially since drawing's not my strong suit. Hopefully you saw the pool as those two different pieces that we needed to look at. So what rate is the water level rising? So we need to think about right now in this situation, we're not up to the rectangular prism yet, right? So we're not filling that part, we're only filling the wedge. So because our height is between 0 and 2, right now we have a situation where we have this rectangular or this wedge with this ratio of my base here being 6 times my height, always, all the time. So I can use that to write my volume formula for that as 1/2 base times height times, and then this is always going to be a width of the pool of 6. So half of 6 is 3. 3 times 6 is 18. H squared, and so this is going to be volume is going to be measured in cubic meters, but I'm not putting the units in there yet, so that's why I'm not writing any units. dV dt is going to be 36H times dH dt, and we know dV dt was given to us as 1/4 cubic meter per minute, and 36, and they're telling us that the water is 1 meter high at that moment in time, and we want to find dH dt. So 1/4 times 1/36, and this is squared. Here, so this is going to be meters squared times meters cubed per minute is dH dt, and meters squared cancel out with meters cubed to leave me with meters, and I have 4 times 36 is 144, so this is 1/144th of a meter per minute is my dH dt. Now to number 21. It's a pretty classic problem. Not going to tell you which problem you're most likely going to get on a quiz or a test, but I would be very surprised if you didn't see a problem like this one that had to do with a right triangle with a rate of change like this, that where you needed to use the Pythagorean theorem. So we're going to have a ladder of 25 feet long that's constant, sitting against the wall. It's slipping down the wall this way, it's sliding out from the wall this way. The dx dt, where this is x and this is y, sliding out at 2 feet per think it's second, 2 feet per second, yes. And we want to find dy dt in this situation. So let's start with x squared plus y squared equals 25 squared, which is 625. I really don't need to know the 625 part. 2x times dx dt plus 2y times dy dt is equal to 0 because the derivative of 625 is 0. I see that constant multiple of 2 that I'm going to divide through by x dx dt plus y dy dt is equal to 0. Every single time that you have a constant hypotenuse, like a ladder here, this is going to be your formula for your related rate for your Pythagorean theorem. So not going to be your related rate when you have this distance over here is also changing. We'll do a problem like that in a little bit with airplanes moving towards each other. So, all right, we're given some information here. So for part A, they ask us when x is 7 feet. Now these all make special right triangles, and I'm just going to assume that you can do the Pythagorean theorem yourself to do what I'm about to tell you, that these are special right triangles. So this is a 7, 24, 25 right triangle that you may have learned about. That's a special Pythagorean triple. So that means that my y is 24. This one is 15 something 25. And so this is 3 something 5. That's a 3, 4, 5 right triangle. So y over 5 is 4. So y is 20. I don't need to do the Pythagorean theorem to find that one. And then this one is the other way around, that this is 24 something 25. It's still a 7, 24, 25. Just the 7 and 24 have switched places. So y equals 7 here. So let's find dy dt. So y dy dt is equal to a negative x dx dt, and dy dt is equal to a negative x over y dx dt. So in each of these situations here, negative x over y. So dy dt is a negative 7 over 24 times, and then 2. Is a negative 7/12, and this is going to be feet per second. In this case here, dy dt is going to be negative x over y. So times 2 feet per second is, this is 3 and this is 4, and 2 goes into 4 2 times. So dy dt is a negative 3/2 feet per second. And dy dt is a negative x over y times 2 feet per second. So that is dy dt is a negative 48 over 7 feet per second. All right, part B. of that problem. Consider the triangle formed by the side of the house, the ladder, and the ground, which I've already drawn. Find the rate of change in which the area of the triangle is changing. So if part B, A is equal to 1/2 base times height, and call that x times y, and then dA dt is equal to 1/2 x dy dt plus 1/2 y dx dt. And when x equals to 7, which is this first situation that we have right here, we have 1/2 of 7 times dy dt we found to be -7/12 plus 1/2 of y we found to be 24, and dx dt was 2. So let's put that into the calculator. 0.5 times 7 times -3.5 plus 0.5 times 24 times 2, and then math, answer to fraction, and I get something I didn't get before. Let me check my work here. So this is half 2 24. Yeah, I typed that in wrong. Nope, I didn't. Then we have half 7 -7/12. That's what I did wrong. That's -7/12. So this is -7 divided by 12. So plus. There we go. So that is going to be 527/24, and this is square feet per second. All right, now this last one's a little harder. I'm going to just go ahead and clear everything and redraw it. It's not really harder, it's just different. So we've got this triangle still. This is x, this is y. We're going to talk about this angle theta. We need to talk about it in terms of radians. So we again are going to talk about when the ladder is 7 feet away from the wall. So x is 7 feet away from the wall. We know that that makes this 24 feet if we need it. And we know that in this case, dx dt was 2 feet per second. And we know dy dt if we need it because we found it earlier in the problem. For this situation is -7/12 feet per second. So let's set up where I'm going to get dx dt because that was given in the problem, not calculated. So cosine of theta is x over 25. 25 cosine theta is equal to x. So -25 sine theta times d theta dt is equal to dx dt. Sine of theta, I'm going to use the specific triangle that we were talking about where this is 7 and this is 24. So -25 times 24 over 25 times d theta dt is equal to 2 feet per second. And this is 25 is going to cancel here. This was feet and this is feet. And these were, anyway, this is going to end up to be unitless. That these feet are going to go away with these feet that are over here. So negative 24 d theta is 2 something, per second there, and d theta dt is negative 1/12, and these are called radians per second. They're unitless, so your theta needs to be measured in radians there. So you're not going to have a unit of feet or inches or square feet or anything like that. When you're talking about an angle measurement, it's its own unit of a real number that's called a radian. All right, that was the last part of 21. Go ahead and look at number 25. I made reference to this just a minute ago about everything in the triangle changing because the planes are getting closer to one another here. And they've drawn the picture there for you with this right triangle. It's going to stay a right triangle. That angle is fixed. These angles are going to change though as the planes fly closer to each other, where this is y, this is x, and this is s. So we have x squared plus y squared is equal to s squared, 2x dx dt plus 2y dy dt is equal to 2s ds dt. So all the 2's can cancel from that. X dx dt plus y dy dt is equal to s ds dt. So we're told that dx dt is a negative 450 miles per hour. Let me let you see that in the problem. That 450 miles per hour for that plane, and the x there is originally 225 miles, and the original y here is 300 miles. And dy dt is a negative 600 miles per hour. That gives me an original s of the square root of 300 squared plus 225 squared. So this original s is 375 miles when I need it, just in that snapshot of a moment. It's going to be changing for sure. So then we have ds dt that we want to find. How fast are the planes closing on each other? Is this distance closing? So we have 225 miles times negative 450 miles per hour plus 300 miles times negative 600 miles per hour is going to be equal to s, which we just found was 375 miles, times ds dt that I'm looking for. So let's simplify. Left-hand side, 225 times negative 450 plus 300 times negative 600. So left-hand side is negative 281,250 square miles per hour equals 375 miles times ds dt. So I'm going to take that number and divide it by 375, and I get an answer of ds dt is a negative 750 miles per hour. How is that going to help me answer my question? So that was part A. Part B says, how much time do I have to have the air traffic controller tell them to take different flight paths so they don't run into each other? So I have a distance of 375 miles that is being closed at a closure rate of 750 miles per hour. It's going to give me a time in hours. The miles are going to cancel, the hours are going to come up. So 375 divided by 750 is 0.5 hours or half an hour, which is 30 minutes that I have to get these planes to, one of them climb, one of them descend, one of them get both of them to turn away from each other, do both, however, as the air traffic controller, I'm going to get them to be on different flight paths, probably getting them at different altitudes and on different headings so that they pass each other with more than enough clearance to make sure that they're not going to collide. All right. I've got number 29 next. So it's pretty normal to talk about a 6 feet tall man in these problems just because 6 is a nice round number, even though most people are not 6 feet tall. We're going to have a lamppost. Here's the light source that's 15 feet above the ground. Somewhere out here is the man that is 6 feet tall, and his shadow is being cast here. This is the shadow that's being cast, right, from the light source, and it's the man is moving in this direction at a speed of 5 feet per second, and we want to know how that's affecting the length of the shadow and how fast the tip of the shadow is moving. So let's go ahead and say that the man is currently 10 feet away from the base of the light. That does not matter at all in this problem, because what we're going to do is we're going to call this distance here x, because this 10 feet is going to be changing. We're going to call this total distance here y, and so we're going to call this distance here, that's the length of the shadow, we're going to call it y minus x. That lamp stays 15 feet tall in the entire problem. You notice again, we have similar triangles, that these are both right angles. The same angle is down here in both triangles, making these angles here congruent and giving us similar triangles. So we know that 15 is to 6 feet, 15 feet is to 6 feet, and I can just get rid of the feet there as, and so these are the heights here. I want the bases here. So 15 feet is the long side here, y is to short triangle here, y minus x. So we have 15 times y minus x is equal to 6y when we cross multiply. 15y minus 15x is equal to 6y. 9y is equal to 15x. And I want to solve for y in this problem. Y is equal to 15 over 9x, both divisible by 3, 5/3 x. So that's going to tell me that dy dt is equal to 5/3 dx dt. This is going to be my answer for part A. Dy dt is going to be 5/3 times he's moving at a pace of 5 feet per second. So that's 25 thirds feet per second that the tip of his shadow is moving. So dy dt is going to be the speed at which the tip of the shadow moves. Because it's related to this distance y here. So for part B, we're going to be asking about the rate of change of the length of the shadow when he's 10 feet away. And again, the 10 feet is not going to matter at all, but we're considering the rate of change of this distance here, y minus x with respect to time. So that's going to give us dy dt minus dx dt is going to be dy dt we just found to be 25/3, and dx dt we have as 5, and those are feet per second. So that is 25/3 minus 15/3 is feet per second, is 25 minus 15 is 10/3 feet per second. And that's your answer to part B. So dy minus x dt is the rate of change of the length of the shadow. Okay. Let's move on to number 37. Uh, 37 is a resistor problem. So 37 says 1 over R is equal to 1 over R1 plus 1 over R2. And so I'll just deal with this as it's given to me, like so, and differentiate that this is negative r to the negative second times dr dt is equal to negative r1 to the negative second times dr1 dt minus r2 to the negative second times dr2 dt, and then all these negatives I'm going to divide out to make them positive. So 1 over r squared times dr dt is equal to 1 over r1 squared times dr1 dt plus 1 over r2 squared times dr2 dt for my rate of change. Given that R1 is 50 ohms, R2 is 75 ohms, dr1 is 1 ohm per second, and R2 is 1.5 ohms per second, that I want to find R first to say 1 over R equals 1 over 50 plus 1 over 75. 1 over 50 plus 1 over 75 is the reciprocal of something. Let's raise that to the negative first power, and I get R equals to 30 ohms. So 1 over 30 ohms squared times dr dt equals 1 over R1 is 50 ohms squared times 1 ohm per second plus 1 over 75 ohms squared times 1.5 ohms per second. So 1 over 900 ohms squared times dr dt is equal to let's just do this, 1 over 50 squared plus 1.5 over 75 squared is 1 over 1500, and this is let's just forget about the units for a second. So dr dt is going to be 900 over 1500. This is going to be in ohms per second. So that's the same thing as 9 over 15 is 0.6 ohms per second. 39 is our last problem for this video. And we have another situation with an airplane. This time it's just climbing. We're given the speed of the airplane in still air is 275 miles per hour. It's climbing at a rate of 18 degrees, assuming that that doesn't change the speed at which it can climb. Find the rate at which it's gaining altitude, which would be dy dt. So here's y, here's x, and we're going to use sine of the angle is equal to y over s. But this is s is this distance here. So s times sine of theta is equal to y. S times cosine of theta times d theta dt is equal to dy dt. So sorry, I did that wrong. Sine of theta is a constant because it's sine of 18 degrees times s is equal to y. Sine of 18 degrees is a constant times ds dt is equal to dy dt. The angle is not changing, the angle is constant. So sine of 18 degrees times my airspeed there is equal to dy dt. So make sure that you are in degree mode here, and 275 times sine of 18 is dy dt is 84.9797, and that's going to be in miles per hour. All right, that's it for this video, and we will come back next time and start talking about 3.1. See you for the next video.